Now, I'm nearly finished reacting masses with you. I'm going to do one more question. A spanner in the works here for you now to see how we'll handle that. They're all the same method. Please, you must get to the stage now of saying, this is not a difficult example or this is not an easy example. I have a method to match this, and I hope you'll find this here as well. This is a variation to the theme now, which I'm going to deal with as well, and I'd need you to be aware of where you're going with this. All right? I'm reading briefly now. Sorry, let me give you a year. 2018, very recently, and it's question 10c. 10c, okay? And I'd like to think that you're given a full balanced chemical equation, and I see a quantity lurking there in the background, so I suspect it's a mole strip again, okay? And we'll work with that. When a rusty object is coated with phosphoric acid, all of the rust taken as iron trioxide, there Fe2O3, on its surface was converted to iron phosphate according to the following balanced equation. The iron phosphate formed was found to have a mass of 4.53 grams. Okay, found to 4.53 grams. And they gave you full balanced chemical equation. There's the rust. The spanner was dipped into a solution of phosphoric acid. And obviously the rust was dissipated or removed from it, very important. And they're asking you all the various questions there now. The iron phosphate was found to have a mass of that. The iron phosphate, they gave it the mass of that. Now, this is the reason I'm doing this question with you. Okay, because you're not given something on the left-hand side, it's on the right-hand side. Fe2O3 is the rust. It reacted with phosphoric acid, H3PO4, by the way, that's on your course, right, that acid. And it goes to iron phosphate, FePO4. And as well as that, you have a byproduct of water. And let's get the balancing numbers right. You have a 2 here, and you have a 2 here. Will you be very careful that you have everything down correctly? Okay, double check everything all the time, please. H3PO4, FePO4, good, and Fe2O3, very good. And they have given you one quantity, which is 4.53 grams. Now, that's unusual. Okay, that's unusual. Now, I must talk to you a little bit about this. I'll be going into a category very shortly on excess reagent. Okay, I'll be doing it immediately after this, so I'm keen that you will have a sense of where you're going with this and that everything is fine, right? So will you take it, please, that we have to work our way through it and make sure that you're able to deal with that. But that's what you're doing there, okay? The rust is removed by the solution, and that's what you got. I'm reading it again for you now. When a rusty object is coated with phosphoric acid, all the rust, Fe2O3, on its surface was converted to iron phosphate according to the following equation. Okay, all the rust was removed, so we'll take it that all the rust was used up, okay? That will be the limiting reagent, all the rust. Because all the rust was used up, okay? You put plenty of that in there, and it will take away all the rust, and there'll be some of that left over, of course. That's the whole idea. So, okay, now that's very important. I'm saying to you that you can read that. All the rust on its surface was converted. All of that was converted to this and this. That's the thing going to run out. That'll be the excess reagent coming up next. Okay? Now they gave us that. So we set up the mole strip. Easy to do that. The ratio strip for a start. 1 to 2 to 2 to 3. Okay? And now, the only quantity you have is that converted to moles. Divide by the MR and you get 0.03 moles. I told you, it'll be cooked in some way, okay? 0.03 moles. So that's going to be 0.03. That's going to be 0.015. And that's going to be 0.045. Are we all okay with that? And they're the moles. Now, as it happens, that's the limiting reagent, okay? And everything is a multiple of that. That's very good. But this time they gave us a quantity here. Convert that to moles, and the ratios have to be right. And there's your moles strip. Now, the question gets very easy all of a sudden. It shouldn't be too bad after that, okay? How many moles of iron were removed from the object, okay, in the rust treatment process? How many moles of iron, okay? So what you have there, you have to be careful now. That's moles of the rust that was removed. 0.015 moles of Fe2 Fe2O3, of Fe2O3. Can you read my writing? Are you okay? Fe2O3. That's not what they asked you though. They asked you how many moles of iron was removed, so you have to multiply by 2. There are 2 irons in every one of them, therefore there is 0.03 moles of iron removed. Okay? Now, very important that you took that out of the mole strip then, and that's what you got. That was that one, 0.03 moles. What mass of rust was adhering to the object before the treatment? What mass of rust? Take that number of moles and multiply by the MR. 0.015, that's the rust, remember? Okay, take that rust, okay, and multiply that appropriately by 160. Multiplied by 160, and you get an answer of, doesn't really matter, 2.4 grams of rust. Now be careful, rust is Fe2O3. Okay, that's your answer. That's that one. Easy enough, yeah? And lastly, what was the minimum volume of a 6 molar solution of phosphoric acid needed to remove all of the rust? Phosphoric acid, that's the minimum number of moles of phosphoric acid needed to remove the rust. So they've asked you a question now. I hope there's something resonating in that question for you. What is the minimum volume in centimeters cubed of 6 molar solution of phosphoric acid needed to remove all the rust? I'm pausing for a minute because I'm hoping that you're onto it. Do you know what I'm going to write next? I don't think I need to say any more to you. That's the moles in there. They're looking for that. You can call it V, okay? They've given you that and you're looking for that. You're looking for that, okay? Put a V in there and you're looking for that, okay? Now don't do what I'm doing. Please write it out a second time. You know what I mean, yeah? Write it out underneath, okay? The number of moles of phosphoric acid are there. That's the exact amount that you needed to use to get all the rust. There'd be more than that, by the way. There'd be some of it left over. That's neither here nor there, okay? And that's exactly what you want. And 5 centimeters cubed is the answer. Put a V in there, 5 centimeters cubed, okay, is the answer. Now that's, I hope that's okay with you. Finally, what volume of liquid water, the density is 1, water. You're here, okay? So you see you're tipping into different parts of the mole strip when you do this. What volume of liquid water, density 1, was produced in the reaction? Now, I need to mention density to you because it's going to come up in a lot of places. I'll get rid of what's here now. I'll get rid of what's here. Now, you see what they've been doing? They've been tipping into different parts of this depending on the question. Each part of the question is a different part, okay? Whenever they give you density, density is mass over volume. Therefore, mass equals density multiplied by volume. Now, I'm saying something fairly profound to you here now. In chemistry, on Leaving Cert chemistry papers, anywhere they mention density to you, I'm nearly certain you're talking about a liquid and you need it in grams. If I was speaking about ethanol to you, I would tell you I had 20 centimeters cubed of it. I wouldn't tell you I had 20 grams. So 20 centimeters cubed needs to be converted to grams so you can go to moles or wherever you want to go. So anywhere you come across density in the chemistry paper, multiply the volume they gave you by the density and you have grams, and then you can get whatever you want from there, right? But you must get grams. Be careful with that one now. Anywhere I'm saying on the paper that they give you density, I'm certain you have a liquid and they've given you the volume of the liquid, but you need to get that liquid in grams. Okay, and that's exactly what you do. And because the density is 1, the volume and the mass would be the same. Okay, and that's what you're dealing with. So 5 centimeters cubed. Are we talking about the same thing? What volume of liquid? Yeah, okay, so you have that many moles, okay, of liquid, okay, and you want to know, okay, so you have moles and you want to go to, you want to work out, they've asked you in this instance, what volume. So get them, okay, you have 0.045 moles of H2O. So you go to grams of H2O by multiplying by the MR. That's 0.045 multiplied by, in this case, 18, okay, grams. Okay, that's good. Okay, you multiply by 18 the MR and you have grams. But they don't want grams, they want centimeters cubed. So that's the same answer in centimeters cubed. Okay, that figure comes out the same. Do I have a result for you? I do. It comes out as, this comes out here as, it came out as 0.81 grams. 0.81 grams. So that's equal to 0.81 centimeters cubed. Now, I'm saying that to you because the density isn't always 1. And if it wasn't 1, then you'd multiply, okay? In this case, you're looking for a centimeter volume, so the volume with the mass, okay? Density is mass over volume, and so you go and solve for the volume. Volume equals mass over density, okay? That'll be fine, okay? If it wasn't 1, okay, you'd have to divide by it. But in this case, it's 1, so they're the same. Just be careful with that, okay? Now, I have to try and get you to be confident that all these questions are the same. If you have very good structure, if you work with the mole strip, you will find it very easy to work on these. And please don't be intimidated by formula or by strange things here. Watch out for the thing with the concentration, will you please? Because that is very strange in one way that we'll be dealing with that, all right? But we have, now that's the end of that category. I'm going to do no more on that. That is reacting masses. I better look at the study plan again with you now to show you where we're going. Now everybody attend to this, please. I have just finished number 5. Okay, I've just finished number 5. I've called it reacting masses, and invariably that question involves giving you a full balanced chemical equation and one quantity called the limiting reagent. And that's effectively what we're after there, okay, more than anything else. Now, I'm about to start another category with you. It's not in the copy you were given. Will you change it, please? That's called number 6. The percentage yield is called number 6 on your copy. Will you change that to number 7? And will you insert number 6 in there, please, as the excess reagent? Okay, that's very important, the excess reagent. Now write that in, please, will you? That we want to make sure that you're dealing with this correctly. That, okay, the excess reagent is an extra category, and I want to segregate them so when you're reading the exam question, you can identify the category that you have. Okay, I don't want to put them all in together. So number 6 is called excess reagent, and I'm going to look at that now. Now, I have a question here on the screen for you. Yeah, you're asked in various instances here to distinguish. Number 6 here on this, I'm asking you to distinguish between limiting reagent and the excess reagent. Now, they're nearly self-explanatory, but you want to be alert. The limiting reagent is the one that dictates everything in the question because the equation's products are all limited by the limiting reagent. When it runs out, you get no more product. The excess reagent as a quantity is fairly useless to us because we've more than we need. We have an excess of it. But you do need to know which is which. Now, the last question I had there, I was able to come to the conclusion that they were removing all the rust from the spanner with this solution of phosphoric acid. Therefore, it's obvious that all the rust was the limiting reagent because when all the rust was gone, no more phosphoric acid would be used up. There'd be phosphoric acid left over, and that's very important, okay? Now, you need to write a note on this because it's not in your notes, okay? It needs to be written separately. I'll take my time while I'm doing it with you because I need everything to be okay. Okay, now here is the question. I'm going to ask you to record the question and I'm going to give you a message for it. This is an easy question. You won't have any difficulties with it, but I need you to take it. Now, are you all ready to write this down? On your A4 pad now, please, you need to write this down. This is an addition to what's in your notes already. Excess reagent. Here's the question. Okay, it reads, 10 grams of iron and 10 grams of sulfur are heated to form iron sulfide according to the following equation. 10 grams of iron, 10 grams of sulfur are heated to form iron sulfide according to the following equation. Now please take down the equation. When you're taking equations down, please leave them stand out on the page. Give a bit of clearance above and below so you can put things in there to mark out for yourself as you go along. And you're asked to show that sulfur is in excess. Show that the sulfur is in excess. Now, if you're looking at the two of them, 10 grams here and 10 grams here, you'd say they're the same. They're not. You'll discover shortly. You'll have some, or one of them will be left over at the end of the reaction. And in this case, it's the sulfur. Okay? If, by the way, if sulfur is the excess reagent, then iron is the limiting reagent. But that's nothing to do with this at the moment now. Show that sulfur is the excess reagent. That's the question. Now, you may well say to me here again, oh, that's a very easy equation compared to a zoorite that we had a while ago. It's the same. Why should one be easy and one difficult if you have a method? And that's where I'm dealing with it now again, please. The method is the method. Will you take the following points, please, as regards how you'd answer this style of question? When you're asked, you're given two quantities in an equation, and you're asked, show me this one is in excess. Have you some idea how you'll do that? I'm going to give you 3 bullet points now, and you should use them all the time. Here's the first one, number 1. Okay, convert the two given quantities to moles. That's number 1. Convert the two given quantities to moles is number 1. Right, step number 2. Construct the mole strip. Construct the mole strip. And number 3, use it, meaning the mole strip. Use it to determine how much of the excess reagent is actually used. Use it, the mole strip, to determine how much of the excess reagent is actually used. And that's it. I'm going to do that with you now. It will make sense when I apply it to the question, but we need to do that, okay? First of all, convert the two quantities to moles. Secondly, construct the mole strip. And thirdly, see how much of the excess reagent is actually used. You'll find you're supplied with more than that, therefore it's in excess. And that's what you do every time. Okay, here we go. We're going to answer this question. 10 grams of iron, 10 grams of sulfur are heated to form iron sulfide according to the following equation. And you're given the equation. Show that sulfur is in excess. Show that sulfur is in excess. Here is the first step. There you go. Will you record that, please? 10 grams of iron. You convert grams to moles by dividing by the AR. Iron is 56, and therefore 0.18 moles of iron. I hope you can read that. 0.18 moles of iron. And the next one. 10 grams of sulfur. Divide by 32. And you get 0.31 moles of sulfur. About 0.31 moles of sulfur. Okay, that's the first part done. Now the next part, guys, okay, we're now going to construct the mole strip. Here we go. Now, this is not easy because the equation is uncomplicated. Doesn't make it easy. Goes to FeS, iron sulfide. I told you a while ago, a compound with 2 elements in it. It ends in IDE, iron sulfide. Okay, by the way, excuse me, that would be iron sulfate. That's iron sulfide. Okay, be careful. Good. Now, and we're told in this instance now, show that sulfur is in excess. They've told us that, so this is the limiting reagent. That's the limiting reagent, and we need to know that whenever we're going to construct the mole strip, okay? So that's the figure going down here, okay? 10 grams. Now, let me say something, please, that's rather important. Under no circumstances, put the other quantity in there. The excess quantity is useless. Because we only use some of it, it's of no consequence to us here. Okay, the excess quantity is useless. It's the limiting reagent you want. Right, and so there's your ratio. Your ratio is 1 to 1 to 1. Convert that to grams, okay? Convert that to grams. And I give you grams here. We're converting that to moles, okay? Convert that to moles. You have 10 grams converted to moles, and what are you going to get? You're going back to where you were there originally, okay? 10 grams is iron is 0.18. So that's 0.18, and that's 0.18. Are you all okay with that? There you go. 0.18, okay? Now here you are. Step number 2, construct the mole strip. You cannot construct the mole strip if you don't know the limiting reagent. Okay, there you go, there you go, there you go. That's fine. Okay, be careful now. There was a 2 there, that'll be 0.36. You understand that? So there you go. Now, what's step number 3? Use the mole strip to determine how much of the excess reagent is actually used. 0.18 moles of sulfur is used, is reacted, is consumed, any of those words in the reaction. But there you go. 0.31 moles of sulfur is supplied. You're finished. Therefore, it's in excess. I'm saying that again. Use the mole strip to determine how much of the excess reagent is actually used. There you are. But you're supplied with more than that, and therefore it's in excess. Now, that's exactly what you want there. There's nothing to it. That's fine. Okay? Now, I've deliberately used that example because it's very easy. It's uncomplicated and there isn't much to it. Can I remind you of the method again now, please? If you're asked to show something is in excess, this question will be recognized. I should probably have said this already. This question will be recognized because you'll be given a full balanced chemical equation and 2 quantities. Not 1 quantity, 2 quantities. This one and this one, 10 grams and 10 grams, you saw there. And they will say to you, show me that this one is in excess. If this one is in excess, this is the limiting reagent. You can set up the mole strip immediately. Convert the 2 quantities to moles, set up the mole strip based on that. Don't you dare put 10 grams in there. The excess quantity is of no consequence to us. That one has to go in there. That dictates everything. And now, thirdly, use the mole strip to determine how much of the excess reagent is used. However, you're supplied with more than that. And that's exactly what you want. Nothing more, nothing less than that. Okay, now that was just to introduce the method. I'm now going to give you a question that's more demanding. This question is in your notes. Okay, can I find it for you? It's at the bottom of page 3 of your notes. Okay, this question is at the bottom of page 3 of your notes, and it is more likely to turn up like that in the exam. Okay, now you've a method. Let's deal with this and see how you'll get about it. Okay, I'm reading the question firstly, and then we'll go back and see how you might handle it and what it would entail. Right? There's nothing to it. No, it's a fairly straightforward question. A student prepared ethanol by reaction between acidified sodium dichromate and ethanol. The quantities used were 17.88 grams. I'm reading the wrong question, am I? A student prepared, no. An excess one we want, yeah. Oh yes, that's coming up in the next question. This one, sorry, I haven't got this one, I'm sure. No, I don't, sorry, I'm thinking of the next category, excuse me. You don't have this in your notes, excuse me. But I'm happy for the moment that you will take it just as a method, because I know there's extra pieces to go in here and you might need at some stage to kind of come back on this, but let me read what's here and show how I'll do it. 80 centimeters cubed of 3 molar nitric acid is poured into 6.5 grams of zinc and allowed to react according to the following equation. Now, will you take it, please? The question I just read out to you will come up in the next category, and I'll be doing it there with you, so you don't need to take this one down. You do not need to take it down. I just want you to see me at work with it, okay? You're given 2 quantities, and you're given a full balanced chemical equation, and you're asked to show that the zinc is in excess, okay? Show the zinc is in excess. Now, I have no problem if you want to take it down now. I have no issue with that, other than I just need you to be alert to a few things in it. There's a couple of things coming up here that could create a problem, and we'd want to have an issue, right? That will be written as molar, right? And that's how it would be. 80 centimeters cubed of 3 molar nitric acid is poured into 6.5 grams. There's one quantity, and there's the other quantity. 2 quantities given and a full balanced chemical equation, and show the zinc is in excess, okay? I am now, first of all, going to say to you, we'll go through the 3 stages of that, okay? The first stage is convert the 2 quantities to moles. There you go. There you go. 6.5 grams of zinc equals 6.5 divided by 65 equals 0.1 moles of zinc. Are you okay? I divided by the MR. And the second one, do you remember our formula again? Here we go. Moles equals centimeters cubed divided by 1000 multiplied by molarity. You'll be given a volume and a concentration, and you are. You're given a volume, 80, and you're given a concentration 3, and there you are. They're the 2 moles. Convert the 2 quantities to moles. Now be careful. I'm reminding you, if you're given a solution, you have to know the volume and the concentration to get moles. In the case of a solid, all you need is the mass. So there's no problem there. So you convert the 2 quantities to moles. Now, that's step number 1. Now, I hope I'm not frustrating you now. That's the question. I'm checking your camera all the time to see is it even legible. I hope it is. Is that all right? I think you can read it all right, can you? 80 centimeters cubed of 3 molar nitric acid is poured into 6.5 grams of zinc and allowed to react according to the following equation. I'm going to take down the equation for you now anyway, and they ask you simply to show that zinc is in excess. Step 1, convert the 2 quantities to moles. I'm going to write out my equation now. There's zinc plus nitric acid, HNO3, goes to zinc nitrate, NO3, twice, plus nitrogen monoxide, plus H2O, and I'll put in the balancing numbers. That's a 4, a 2, a 3 for that, an 8 for that, and a 3 for that. Will you be very careful, please? Take great care that you have it down correctly. I must have said this 4 times already today. Okay, will you be careful? That's 3, 8, 3, 2, and 4, very important. All right? Now, show that zinc is in excess. So this guy is the limiting reagent. This guy is the boss. Show the zinc is in excess, that's the limiting reagent, very important, okay? So I'm writing that down for you now. You were given 80 centimeters cubed of 3 molar nitric acid. You were given that quantity. Let's construct the mole strip, okay? Ratio for a start, 3, 8, 3, 2, and 4. And moles then underneath now, moles. Now you convert that quantity to moles, okay, we've done already there. 0.24 moles for that. Now, 3/8 of that, 1/8 of that is 0.03, 3/8 is 0.09. That's the same, 0.09. That's 0.06. That's half of that. That's 0.12. Are you okay with that? Now be careful, take your time with that. Now that is the limiting reagent. The limiting reagent dictates the mole strip. Okay, very important. Everything must be a multiple of that. That is the one that's going to run out. And so that's the amount of that you need. That's the amount of these you'll produce. Very important. That's your mole strip. Now, that's step number 2. Let me repeat again now. Step 1, convert the 2 quantities to moles. We've done that. Next, set up the mole strip. You cannot set up the mole strip if you don't know the limiting reagent. You do, because they asked you to show that that was in excess. They asked you that. So therefore, look, that's the limiting reagent, and there's your mole strip. And step number 3, are you watching me now, please? Step number 3, use the mole strip to determine how much of the excess reagent is actually used. 0.09 moles of zinc, right, is used, is reacted, is consumed, any of those words. But 0.1 moles of zinc is supplied. Okay, I want to put a note in there as well, that's okay. That's a bigger number than that, at the risk of insulting you all. Now, in exams, they tend to have them very close. I had one there a while ago and there was enough for the whole nation, you know. Will you take it, please? Excess could mean any amount once it's bigger, but that's bigger than that, therefore in excess. And that's it. Now, please, I want to talk to you about the method again, because that will be carrying quite a few marks now. You're given all those quantities. If you're asked you're given 2 quantities and you're given a balanced chemical equation, and the question asks you, show me that that's in excess. Show me that that's in excess. If that's in excess, that's the limiting reagent. Convert the 2 quantities they gave you to moles. First thing, one there, one there. Secondly, construct the mole strip. You can't do that if you don't know the limiting reagent. If you know the limiting reagent, then that's the mole strip. And thirdly, use the mole strip to determine how much of the excess reagent was actually used and you'll find you were supplied with more than that, therefore it's in excess. That's the amount that was actually used in the mole strip. That's the amount you're supplied with. That's bigger than that, so therefore it's in excess. And that's exactly what you want. Now, they don't get any more difficult than that, and that's not bad at all, that you have to be aware of that. Now, there is one variation to this I'm going to do with you. I'd be keen to keep it, if I can, on the same video, and it is where sometimes you're asked which is the excess reagent, and that can create its own issues. We'll just have a look at that, okay? Make a note of the year, please. 2016, question 11A. 2016, question 11A. Now I'm reading that for you. Sorry, now I'm kind of conscious all the time that you may have difficulty in reading the question from the screen, but will you make a note of the year, everybody? I keep telling you that so that you can dip into it yourself in your own time. But it's important that you know that you're investigating the question, that you're reading it fairly closely. A mixture of potassium nitrate and sulfur reacts according to the following balanced equation, and they've given you a full balanced chemical equation there. One of the two reactants is in stoichiometric excess. Isn't that lovely? It's in stoichiometric. We're doing stoichiometry at the moment. It's in excess. When 20.2 grams of potassium nitrate are mixed with 24 grams of sulfur. So they gave you the two quantities, 22.2 grams of this, 20.2 grams of this, and 24 grams of that. And they're asking you then, which reactant is in excess? Now, we need to have a strategy for that. Okay, it's the same question, by the way. There isn't a lot of problem in it. Okay, I'm going to start with it then for you. I'm going to write out the equation. Okay, two quantities, by the way. I should probably start with that first. Okay, 20.2 grams of potassium nitrate, KNO3. Okay, and I have converted that to moles because that's what we do first of all. 20.2 divided by 101 is going to give me 0.2 moles. 0.2 moles of KNO3. I hope you're okay with that, of KNO3. Is that all right? That's that part of it. Okay, 20.2 moles of, 20.2 grams is equal to that many moles. Divide by the MR for that, okay, happens to be 101, and you'll get that, okay? That's okay. And the other one then is 24 grams of sulfur. 24.0 grams of sulfur is equal to 24, I might as well write this one out, divided by 32, be careful, is equal to 0.75 moles of sulfur. Okay, and there are the two you have. You have potassium nitrate and you have sulfur, and you're given two quantities, okay? Convert the two quantities to moles, very good. Now, I'm going to take the mole strip for a moment, I'm going to write out the equation. 4 KNO3 plus 5 sulfur goes to 2 K2O plus 2N2 plus 5 SO2. Now be very careful, won't you? A 4, a 5, a 2, a 2 and a 5. Be very careful with that. Okay, the two reactants are given to you, we have them there. Now, which of them is in excess? And we have to work on that. Now, you can do it by many methods, it doesn't really matter. Okay, it doesn't really matter. What you'll do is take the ratios here for a moment now and see how you work on that. Forget about the mole strip a moment. Okay, the question is asking you now, which reactant is in excess? In other words, is it the KNO3 or is it the sulfur? Which of them is it? And that's what we have to deal with, and I'm going to deal with that now. If you took 0.2 moles of KNO3, it will require, and watch this now, the ratio is 4 to 5. Can you see that? Ratio is 4 to 5. It'll take 1 1/4 of that. Are you okay? That's what it'll do. Okay, and that's what you're doing. It will require 0.25 moles of sulfur. I'm going to say that again. The ratio is 4 to 5. I took the first quantity they gave me. Okay, 0.2 moles of that. 0.2 moles of that will require 0.25 moles of that. 4 to 5. Ratio 4 to 5. Are you okay? That's the number of moles of sulfur we require. But you're supplied with that amount, but 0.75 moles of sulfur supplied. So the sulfur is in excess. Now, I'm going to say to you, supposing that was smaller than that, well, you'd say, well, then the other one was in excess. Like either that, the amount supplied is greater than the amount you need for it to be in excess, or it's not. So you do one of them, and it came out that way. Now it happened to be that way. If this came out to be, supposing that came out to be, we will say 1.5 moles. You require 0.25 moles, but you've only 1.5 moles. Therefore, this is the limiting reagent then. I'm saying that again to you now, ratios 4 to 5. I took the mass of first one here, converted it to moles. 0.2 moles of that requires 0.25 moles of that, 4 to 5. I need 0.25 moles of sulfur, but I'm supplied with 0.75, and therefore that's the answer. Okay, therefore it's in excess. I know then that that's in excess. Now go back in that again just to see where I'm at, okay? Take the first one and see how many moles of the second one it will need, and are you supplied with more or less than that? If you're supplied with more than it, it's in excess. If you're supplied with less than it, it's the limiting reagent. So the other one is in excess. Okay, this is my left hand, this is my right hand. Okay, it's as simple as that. There's only the two of them there, and that's it. So we know now that the sulfur is in excess. Which of the two is in excess? And you're fine with that, are you? That we have that. The sulfur is in excess. Now it's based on numbers only. There's nothing else. Okay. So sulfur is in excess. Which reagent is the sulfur? So that's the limiting reagent. So that allows me, and it says what mass of that reactant is unused. What mass of it is unused? That's the amount you require. That's the amount you're supplied with. Subtract one from the other. 0.75, 0.25, 0.50 moles. And it moles of sulfur. And it asks you what mass. So you take the 0.5 moles and you have to multiply that by its AR. Are you okay with that? That there is no issue with that. 0.5 moles equals 16 grams, okay? You multiply it out, okay? Sulfur is 32, okay? You're multiplying it out there, whatever you're getting for that. Are you all right with that, everybody? That's what you're going to get. You get 16 grams. Okay, that many moles of sulfur multiplied by its AR, and you have the answer. That's that part. Next, calculate the total volume of gaseous products. The volume of gaseous products. Now we need the mole strip. Now you need the mole strip. So here we go. I know the limiting reagent. The reagent is that. And I was given 20.2 grams. Ratio 4, 5, 2, 2, 5. Okay, convert that to moles. Moles, it's converted there for you. And that is 0.2 moles. Now be careful. 0.2 moles, therefore that's 0.25 moles, that's 0.2 moles, that's 0.2 moles. And this one here is no, that's not right, silly man. That's 0.1, that's 0.1, and that's the same as that 0.25. Are you okay with that, everybody? That's what you want. And it asks you, calculate the total volume in litres of gaseous products measured at STP formed in the reaction. That's an S there. Okay, sorry, no, I didn't put it in my own. That's a solid, that's a gas, and that's a gas, you're told that. So these two you're dealing with, okay? They're the two you're dealing with. So you have 0.1 moles of nitrogen, okay, 0.1 moles of nitrogen multiplied by 22.4, and you've 0.25 moles of the other gas, which is sulfur dioxide, multiplied by 22.4. Add them up and you are going to get your answer there, okay? You end up getting the total is the gases together, yeah, they come out as 7.84 litres of gases. You can't label them in this case because some of them is nitrogen. Okay, there's a gas there, there's a gas there. Now, the wording is very important. The total volume in litres of gaseous products, okay, measured at STP. So you evaluate the two of them and add them together to get your total volume. Okay, your total volume. And lastly, what mass of solid is produced? There's an S after that, I told you. There's an S there. So you're taking that many moles and multiplying by the MR for that. That comes out to be 9.4, excuse me, 9.4 grams of K2O. Okay, now that's a strange question, but I want you to see a bit of variation in it. Will you in your own time revisit that, please? It will be very important that you would do that, because that is basically what we're dealing with there in terms of excess reagents. All right.